All right, as we continue our lesson on simplifying square roots, the last video we talked about uh, the different numbers, rational, irrational numbers, integers, whole numbers, and how we classify all those. We also talked about perfect squares. We're going to use perfect squares as we simplify square roots. So as we talk about that, square roots are in simplest form if it meets a list of factors or different criteria. First of all, there can be no perfect square factors other than 1 in the radicand. Radicand is that little symbol. No fractions in there, and no radicals in the denominator. So we'll work on fixing those three things in order to put radicals in simplest form. So first of all, we're going to take a look at the product property. Product property says the square root of a product equals the product of the square roots. So for example, square root of 4x is equal to square root of 4 times square root of x. This is similar to, let's say we had the number 18. I can represent 18 as 2 times 9. I haven't changed the number, I've just broken the number apart into a different way. So I can do the same thing with the radical. Just I can break it apart as long as I keep the radicands above. So let's do that. Square root of 32. So when we do this, when we break it up, we want to think of it, kind of like a factor tree, and think of finding perfect squares because that's going to make our life easier. So if I think back to those perfect squares, well, 32, I can say square root of 16, because that's a perfect square, times square root of 2. And when I break it into that factor, I see, well, square root of 16 I know is 4. And it's the same thing, so I can just change it to make it look like what I want it. We want to take out as much as we can from under the radicand. And at that point, 4 is as far as that can go. Square root of 2 is not a perfect square, and I can't factor anything else out, so I have 4 times square root of 2 will be the square root of 32 in its simplest form. Square root of 9 and square root of x cubed. Well, I can break that down into square root of 9. So that's a perfect square. Times square root of x squared. Because that's a perfect square. And square root of x. Well, square root of 9 is 3. Square root of x squared. The radical and the square cancel each other out, so we just have x. And square root of x I can't take, so I could just leave that. So I have 3 times x times square root of x. And when I put that all together, I can just list it 3x square root of x. Typically, we put all the values outside the radical first, and anything in a radical goes afterwards. Next, we're multiplying radicals together. So let's say we multiplied 6 times 6 together. I would just multiply that, and I would get 36. Now when I'm multiplying, if they're under the radicand, it's going to stay under the radicand. So it'll be square root of 36, which is a perfect square. Square root of 36 is 6. And you should start being able to recognize those perfect squares. The next example, I have square root of 3x times 4 times the square root of x. Now, with multiplication properties, we can rearrange. They're commutative. We can multiply whatever we want together since we're multiplying everything together. So I'm going to multiply the 4 first since it's not under a radicand. And then I have square root of 3x and square root of x. Okay. And remember, now that we have these under the radicand, I can combine those together. So I have 4 times square root of 3 times, and x times x is x squared. We get more of that once we get into exponents later on. Now, it's kind of a sloppy 3, but now I can break it apart. So when I do that, I'm just going to move my next examples down. I want to make sure that I break it apart. So the 4, that can stay as a 4. Square root of 3, I can factor that out. And square root of x squared, I can factor that out. The only one that's a perfect square is square root of x squared. That becomes x. And I still have 4. And I still have square root of 3 because that's not a perfect square. So when I simplify it all, I'm just going to rewrite it all nice and neatly. And I'll put whatever's not under the radicand first, so 4x. So write that over here. And square root of 3 is under the radicand, so that goes at the end. So 4 times x times the square root of 3. That's how we would simplify that one. Our next example, notice we're multiplying, and we're going to have to use the distributive property. So square root of 5 times square root of 10, both under the radicand, so that'll be square root of 50. And then square root of 5 times positive 2. Well, 2 is outside the radicand, and the 5 is underneath, so it's going to be 2 times square root of 5. Now I got to look, can I simplify square root of 50? If I'm looking at my factor tree, I can break it up into, I know 50 is 25 times 2. 25 is a perfect square. I'm going to break that apart. And this, I can't break it down any further, so I'll just leave that for now. Square root of 25 is 5. And square root of 2, we can't break anything apart from that. So that will give us 5 square root of 2. Then I'll just bring down positive 2 square root of 5. So we'll simplify as 5 square roots of 2 plus 2 square roots of 5. I'll have you try this next one on your own. Why don't you pause the video, try the next example, and restart the video when you're ready. All right, so I distributed 5 square root of 15 times 2. 5 times 2 is 10, and square root of 15. Then I distributed 5 square root of 15 times square root of 5. 5 times square root of 75, since 15 and 5 are both under the radicand. 10 times square root of 15. Square root of 15 I can only break into 5 times 3. Neither of those is perfect, so I can't break those down any further, so I'll leave that. And then square root of 75 I can break into square root of 25 times square root of 3 times 5 still. So it's 5 times square root of 25 times square root of 3 now. Square root of 25 is perfect, and it becomes 5. So I have 5 times square root of 3. 5 times 5 is 25. So that gives me 25 times the square root of 3. Next, let's apply the quotient property of radicals. When we take the square root of a quotient, it equals the quotient of the square roots of the numerator and denominator. So what that means is if I have square root of 16 over square root of 25, I can break it down to square root of 16 over the square root of 25. Square root of 16 is 4, square root of 25 is 5. So anytime we have square root of a fraction, we can make it the square root of the numerator over the square root of the denominator. We always need to get the denominator rationalized. There cannot be a square root in the bottom. So luckily square root of 100 is 10. Square root of 13 is not a perfect square, and I can't take anything out. So we can just leave it. It's okay to have a radical in the numerator, but not the denominator. Next example, we would say square root of 7 over square root of x squared. Square root of x squared in the denominator is x. Square root of 7 is not perfect, can't factor out, so it's just square root of 7. That's how we can use the quotient property. We're going to apply that now in order to do what's called rationalizing the denominator. Tough to say. That's how we eliminate the rational expression from the denominator. Maybe you get the governator to do that for you. But you probably don't know who Arnold Schwarzenegger is anyway. But anyway, if this is not a perfect square, what we do is we rationalize it, make it a rational number. Remember, this is an irrational number, so let's make it rational. So we're going to multiply by 1. And because multiplying by 1 doesn't change anything. And you know that, you've learned that. That's a property that you've learned with multiplication. So let's change 1. Let's use 1 as square root of 7 times square root over square root of 7. because square root of 7 divided by square root of 7 is 1. We're really multiplying by 1. We're not changing anything. But the neat trick about this is what happens now that we're multiplying square root of 7 times square root of 7 is we get square root of 49 on the bottom. And we'll find out what happens when we have square root of 49. And on the top we have 5 times square root of 7. The nice thing now is what square root of 49 is 7. It's become a rational number. We've rationalized the denominator. A lot of big words for you today. We have 5 times square root of 7 over 7. This can't be simplified because 5 and 7 cannot be divided by the same factor. We would be done. So when we do that, we want to multiply by what's in that numerator, what's in the denominator, so we can rationalize it, make sure to multiply the same thing on the numerator. So here, square root of 3b, there's nothing we can simplify that by, so let's multiply by 1. And in this case, 1 is going to be square root of 3b, and square root of 3b over square root of 3b. It's the same thing times itself. What happens? We get square root of 3 times 3 is 9. B times b is b squared. At the top we have 2 times 3 is 6. And b. Square root of 9b squared. Square root of 9 is 3. Square root of b squared is b. So 3b. And we still have square root of 6b since there's nothing we can factor out of that. So square root of 6b over 3b. It's easier to work with now because we don't have any irrational number in the denominator. And the last thing we need to talk about is adding and subtracting radicals. Just like when you add or subtract anything in algebra, you need to add or subtract like terms. So like radicals. So this is 4 times square root of 10. This is negative 9 times square root of 10. Similarly, if we had 4x minus 9x, we can combine those because those are like terms, and that would give us negative 5x. In the same way, 4 square roots of 10 minus 9 square roots of 10 is negative 5 square roots of 10. And then we have plus square root of 13. It's not a like radical, so we can't combine it. So we would leave that as it is. 5 square roots of 10 plus square root of 13. Next example, you notice we don't have any like radicals. Well, that's probably because we haven't simplified yet. 5 square root of 3, that can't be simplified. But I'm guessing square root of 48, we can simplify. Think of our perfect squares. We've got 4, 9, 16, 25, 36, 49, 16. Sounds about right. 16 times 3. And square root of 16 is 4. Square root of 3 is not perfect, so we have 4 square root of 3. So really, this is 5 square root of 3 plus 4 square roots of 3. And we have like terms. 5 times the square root of 3 plus 4 times the square root of 3 gives us 9 times the square root of 3. And that's it. You've learned how to simplify radicals by using the product property and separating them into different factors, looking for perfect squares, applying your previous knowledge of factor trees. You know how to multiply and distribute radicals. We know how to use the quotient property and separate them when they're square root of a fraction. We know how to rationalize the denominator, and finally, add and subtract. So we'll do some practice in class. Until then, I'll see you later.